Good afternoon, all. I'm going to walk you through some of the setup for the Fighting the Height of the Ceiling lab and some of the procedures so that you're not confused. This lab is building on the idea that we can determine a measurement indirectly by measuring other quantities and then relating them through some physics. You don't have to understand the physics at this point. I just want to illustrate this exercise by having you make 3 measurements about a lacrosse ball, especially its fall, and then use it to find the height of the ceiling. Once you do that, then I'm going to have you measure the height of the ceiling using a meter stick to see how close you are. Then we can discuss your results next time we meet. Okay, so what I want you to do is right now fill out the very front of the lab together so that you again have a proper context. I got to give you the relevant equation, which you have no idea about right now. And then I'll talk to you about the how you're going to measure certain things. Okay, so I've already talked about the purpose of the lab. Okay, and so one of the things we would have done in class is we would brainstorm how much time a ball falls in the air is affected by what. Okay, so if I drop something and it's going to be in a certain time, there's a reason it's what fell for that time. So what are those quantities that might matter? And then we'll take the relevant quantities and put it into an equation. It relates time to those quantities. That's basically what physics does. So obviously we can't brainstorm, so let's just talk about some things that might come to your mind. Perhaps the most obvious thing, even if it's not the first thing, is simply the height, right? You know intuitively if you drop something from a greater height, it's going to take more time. And so in our lab, we know that height is the main purpose of this to find. So I'm going to put a slash and put a variable for what that's going to be represented in the equation. So height is going to be h, which makes sense. Some of you might be thinking, well, something about the ball matters, and it does, or maybe it does. Well, let's test it out. So we're going to say one measurement of the ball that might matter is the mass, and that's m. Another thing that might matter is how big it is, and that big it is could be volume. Okay, capital V. Another related quantity that's not the same as mass, but related to it is weight. And we're going to give this an unexpected symbol, F sub G. F is for force, G is for gravity. So that's just one variable. You might think the shape might matter. Okay, and don't ask why, we just give it that a symbol of C for coefficient. I'm thinking of other things that have come up through the year's surface area. So that's a lot of things that could possibly affect the fall of a ball at the time of flight. So what we're going to do is we're going to try to simplify this. And the key word here is freely. And again, we'll learn this physics down the road. But freely means that we're taking out the effects of air. So if you take the effects of air, and air shouldn't have much of an effect in this particular lab, then we can reduce the factors that affect the time in the air to 3. It would be the height that it falls, the mass, and the weight. And that's what we're going to test. So you can see that I've kind of rewritten them down there. So what I'm going to do now is give you an equation that relates them all in terms of time. So we can say the time that an object is in the air, okay, is equal to the square root of twice the mass times the height divided by the weight. Again, you don't have to know where that comes from. We will learn that physics a month or so from now. The point, though, is if we know 1, 2, 3, we can predict time. But that's not the main goal of the lab. The main goal is kind of alternative to that, and that is if we measure time, mass, and weight, we can figure out the height. So one of the things you're going to have to eventually do is rearrange this whole thing algebraically and solve for h. And that's where your algebra skills are going to be important. Okay, so I have here the list or a procedure of what you're going to do. Basically, you're going to get a partner, okay, and with the class, we should be able to do 7 groups of 2, maybe 1 group of 3. You're going to drop an object. That object is going to be a lacrosse ball. The lacrosse balls are in a white bucket next to the window, okay, and you're going to hold it against the ceiling, and you're going to drop it to the ground, and you're going to time its flight. and then you're going to measure the object's mass using a balance, and then you're going to determine the weight using a spring scale. And I can't show you in this situation, but I can talk to you about how to use them. So read these carefully. Normally, if I was here, we would do a preliminary practice with timing. I suggest you still do that, but I'm not going to make it a formal thing. So before you start recording times, in other words, before you start dropping and recording, you should practice a system with your partner or partners such that you know you're timing the actual flight and not being too slow. And that's usually not the problem. It's usually being too fast. Kids tend to anticipate when the ball is going to hit the ground because they're so worried that they're going to be late that they end up giving a really, really short time. So really practice that you start the stopwatch as soon as a person releases it, and you stop it as soon as it hits the ground. And so, speaking of stopwatches, I'll have them in the front of the room. You can use your stopwatches on your phones if you want. All right, so let's talk about the data. So you're going to time for the lax ball to drop. I've got one that's like 10 trials, and then you're going to do an average. And don't record those trials until you've done practice. You feel you're comfortable that you are timing the exact flight of the ball. Do not, so when you're doing data, you can't just throw out data that you don't like. If you're going to throw out a data point, it has to be because the person dropping released it before the timer was even paying attention, or the buttons didn't work. So you can't look at your time. So let's say you get a time of 1.3 seconds, and then you get, actually, I don't want to mislead you to think that it's going to be that long. Let's say you get a time of 0.76 seconds, and then another time you get 0.64 seconds, 0.65, and 0.63, and then you say, wait a second, this doesn't fit. You can't do that. You have to keep it unless you have a good reason to think that it was wrong. So you're going to probably get a decent amount of variation here. You want to minimize that, but don't throw something else because it doesn't fit unless you know you physically did something wrong when timing it. Okay, so I expect this measurement to be the worst measurement, the one that's going to be the most off. So one way we can help reduce the chances of being inaccurate is once you have an average time for your group, and round it to the nearest hundredth of a second, because that's what your stopwatch does. So if your average time is 0.86, then, or let's say the average on a calculator turns out to be 8.865, just round, or let's say 0.8658, round that to 0.87. And then what you're going to do is share this with the class, either on the whiteboard or just talk to each other. And so we're going to take the average times for each class, share them, and then we're going to get an average of an average. And this is what you're going to base your height on. So hopefully if one group is too long in timing and the other group is too short, it all averages out to something that is close to what it should be. Okay, it's not perfect, but I think it gives us a better chance. So once you do all the timing, we got to get the mass and the weight of the ball. Okay, so again, I can't show you, but hopefully this is going to be somewhat familiar for you. So I just have to point out where they are, and you should be fine. So mass is simple. You can use an electronic balance. So you'll see around the room a few electronic balances. Put the ball on there, and you should be good to go. Now, of course, that's going to measure your mass in grams. Okay, so put all the digits. So let's say it turns out to be 433.5 grams. Then you're going to convert that to kilograms, because this is what has to go in the equation. You have to put kilograms in your equations. So make sure you do the metric conversion that properly. Don't make a silly mistake on it. All right, so weight is different. You're not going to use the balance. You're going to use a spring scale. So in the back of the room, you will see some green spring scales. They're tubes. Right? They have a little hook on it, and they have some markings. There's markings on both sides, so it's really important you read the side that has the N at the bottom right here. What are the units for weight? And N stands for newtons here. So what you're going to do is you can't really hang a ball directly from a hook. So also back there you will see a bag of some sort, plastic bag, okay? And you're going to hang that plastic bag, weigh it. It should have a very small weight on this, and then you're going to put your ball in it, okay, and then just subtract off the weight of the bag, and there you have the weight of the ball. All right, it's a simple technique. So either use a plastic bag, or if there is none of those, use a paper bag. Alrighty, so once you have all the data, then you're going to take the equation from the front. So now I'm down here in calculations. In the theory section, I gave you that equation for how time is related to height, mass, and weight. And you're going to rearrange it algebraically and come up with an equation for h in terms of these three variables. This is where our algebra skills are really important, so work together on that if you're not so sure. Then you're going to plug in the numbers, and you're going to get a height of the ceiling, and that height hopefully makes sense. So if you think of your estimation skills, you have a pretty good idea of what the height should be around. All right, and then if you get an answer that's consistent with that, that usually is a good sign. If you get something that's way off, then either you did your algebra wrong, or you did something weird in a calculator, or less likely you made a mistake in your measurements. Okay, so once you have that round to the nearest 100th meter, and you're going to put the experimental height right here. Once you have that, and this is with your own group now, this is not as a class, then you're going to get a meter stick, and this is the next page, and you're going to measure the height of the room with that meter stick, and you're going to record it here. Now, to be a little bit more accurate, once you get that height, you have to subtract off the diameter of the ball, because if you think about it, if this is the ceiling and this is the floor, and the ball was here, really what you timed was from here to here, the bottom of the ball to the bottom of the ball. So we want to subtract off this distance there from what you do with the meter stick. That will give you more accurate. It's a few centimeters difference, but anyway. And then the rest is pretty straightforward. We have percent differences. How far off are you? And I don't expect you to be perfect, but that's all right. And then give me a good discussion on which one you felt was the least accurate measurement and why. And then what could you do to minimize that? Okay, so good luck. This should be a fairly successful lab. Help each other out if you get confused.